Saiza and I will start this presentation. But first, we must know what non-inertial reference frame is. Non-inertial is a frame that is accelerating with respect to an inertial frame. For example, say you have a rocket that is in space and a person on Earth is watching the said rocket. The rocket is non-inertial frame and the person on Earth is the inertial frame. Non-inertial frame can be both linear or rotational, and with the existence of non-inertial frame, there exists fictitious frame force, which is apparent force that arises when observer is non-inertial frame is accelerating. In this condition, Newton's law cannot be used, thus it is necessary for fictitious force to be applied so that Newton's law can be possible to use. Few examples of fictitious force include centrifugal force, Coriolis force, and Euler force. We will now see few situations of non-inertial reference system, starting with accelerated coordinate system with the formula small r equals to r plus r prime, where small r is position vector of particle p, r prime is position vector in moving system, and r is displacement of the moving origin. Once we derive it once and twice, we will get both the velocity and acceleration where v and a are respectively the velocity and acceleration of the moving system. And v prime and a prime are the velocity and acceleration of the particle in the moving system. If the velocity is constant, a will be 0, thus making a equals to a prime. But if the system is accelerating, f equals to fa becomes f equals to m in bracket a plus a prime. Moving ma prime to the right hand side, we will obtain ma prime equals to f minus ma as non-inertial reference frame formula. Next two subtopic, we will talk about rotating coordinate system where rotation direction is denoted by q and rotation instantaneous angular speed is omega. Combining both, we will obtain rotating system angular velocity omega q. Since both coordinate fixed and moving have the same origin, we will say r equals to r prime. But before we can differentiate it to find velocity, I prime, j prime, and k prime are not constant, thus making there exists x prime di prime over dt plus y prime dj prime over dt plus z prime dk prime over dt. Or it can also be known as velocity due to rotation of the prime coordinate system omega cross r prime. With a few methods, once we differentiate velocity, we will get a equals to a plus omega dot cross r prime, which is the acceleration translation, plus 2 omega cross v prime, acceleration Coriolis, plus omega cross r prime, acceleration centripetal. The next slide shows exactly almost the same thing, except it is on force and there exists mass on all three accelerations.
The first example of non-inertial system is an accelerating car. When a car accelerates forwards, observers or passengers in the car will feel as if they've been pushed back into their seat. This sensation is due to the fictitious force that appears to act on passenger in the opposite direction of the car accelerations. From the perspective of observers inside the car, this fictitious force is the opposite of the acceleration, which means that F fictitious equals to the negative ma. The video shows two situations. The first video shows that the path of the ball thrown was in a straight line, while the second video shows that the ball's path was curved. How does this happen? Well, let me explain. The first video shows the perspective of observer on the ground. The ball moves in a straight line due to its inertia, assuming no other forces act on it, which makes the observer see the path of ball in a straight line. While for the second video, it shows the perspective when the observer is on the merry-go-round. The ball appears to curve from the observer's perspective due to the Coriolis force. The Coriolis force acts perpendicular to the direction of the ball's velocity relative to the rotating frame. This results in the ball's path curving in a direction opposite to the rotation of the merry-go-round from the observer's point of view. This also could happen due to the centrifugal force, where a rotational reference frame seems to push the ball outward away from the center of rotation. The last example is accelerating elevator. Did you realize when we enter an elevator that accelerates upward or downward, we felt a little heavier or lighter? Well, if the elevator accelerates upwards, the observer feels heavier than usual because in addition to the gravitational force acting downward, there is an additional a viscous force acting downward due to the upward accelerations of the elevator, which makes the apparent weight of the observer is greater than the actual weight, where apparent weight equals to mg plus ma. While when the elevator accelerates downward, the observer feels lighter than usual because the viscous force acting upward due to the downward accelerations of elevator opposing the gravitational force. The apparent weight of the observer during acceleration is less than the actual weight, where the apparent weight equals to mg minus ma.
Assalamualaikum warahmatullahi wabarakatuh. I am Ayu Najah binti Rashid and I will continue this presentation by discussing the question example. As we all know, each group must choose one problem at the end of the related chapter and show how to solve the problem. Therefore, the source of the problem of our group is the textbook Analytical Mechanics 7th edition, page 225, problem number 5.2. However, we did change the value of the problem. So, here is the problem. An ultracentrifuge has a rotational speed of 600 revolutions per second (rps). A. Find the centrifugal force on a 2 micrograms particle in the sample chamber if the particle is 6 centimeters from the rotational axis. B. Express the result as the ratio of the centrifugal force to the weight of the particle. Before we answer the problem, it is better to list down all the values given and convert it into standard units. First, rotational speed omega is 600 rps. We need to convert 600 rps into radian per second, which we can get by times the value with 2 pi radian per rps. Hence, omega is equal to 1200 pi radian per second. Second, the mass of the particle m is 2 microgram equal to 2 times 10 to the power of negative 6 gram, which equal to 2 times 10 to the power of negative 9 kilogram. Third, the distance from the rotational axis r is 6 cm, which equal to 0.06 meter. A. Find the centrifugal force on a 2 micrograms particle in the sample chamber if the particle is 6 cm from the rotational axis. The formula for centrifugal force is given by the expression Fc equal to the mass times the square of the rotational speed times the distance from the rotational axis. Given that m is 2 times 10 to the power of negative 9 kg, omega is 1200 pi radian per second and r is 0.06 meter. Substituting this value into the formula, we get the centrifugal force equal to 1.706 times 10 to the power of negative 3 newtons. B. Express the result as the ratio of the centrifugal force to the weight of the particle. The formula of the ratio of the centrifugal force to the weight is given by the expression centrifugal force Fc divided by weight W. From this formula, we need to find the weight first. The weight of the particle is given by W equal to mass times the acceleration due to gravity. Substitute the value of mass 2 times 10 to the power of negative 9 kg and the acceleration due to gravity 9.81 meter per second squared. We will get the value of W 19.62 times 10 to the power of negative 9 newtons. After that, substitute the value of W and Fc into the formula of the ratio, and the ratio will be 8.695 times 10 to the power of 4.
So that is all from our team. Is there any questions?
May I ask a question? So, what's the difference between centripetal and centrifugal force?
Thank you for the question. So centripetal force is observed from an initial frame of reference and it's pulling object towards the center. Meanwhile, centrifugal force is observed from a non-inertial frame and it's pushing object away from the center. So that's the major difference between centripetal and centrifugal.
I see. Thank you for answering.
You're welcome. Is there any other question?
I would like to ask, why do riders on a merry-go-round feel like they were pushed out from the merry-go-round?
Okay, so riders on the merry-go-round feel an outward force due to the rotation of the systems. This force is called as the centrifugal force, which is a fictitious force that arises in the rotating reference frame. It is not a real force, but it an apparent one that results from the inertia of the riders' bodies, resisting the centripetal acceleration required to keep them moving in a circular path.
Okay, thank you.
Okay. So before we stop, is there any other question?
I would like to ask a question. Why did your group choose the ultra-centrifuge problem as your problem?
Okay, this is because the ultracentrifuge problem relates to all the three types of coordinate system. Therefore, the ultracentrifuge problem's nature and forces make it applicable to all three types of coordinate system.
All right, thank you for your answer.
For conclusion, this is what we can conclude from chapter 4. A non-inertial frame is accelerating relative to an inertial frame. Non-inertial frame can involve either linear or rotational acceleration, and fictitious force arise within these frames. There are three subtopics under this chapter, which are accelerated coordinate system, rotating coordinate system, and dynamics of a particle in a rotating coordinate system. In an accelerated coordinate system, we will obtain m dot a prime is equal to f minus ma as a non-inertial reference frame formula. Meanwhile, the formula of Coriolis acceleration, centripetal acceleration, and transverse acceleration are what we will get in rotating coordinate system, and the formula for all of these acceleration are just like what you guys can see on the slide right now.
For dynamics of a particle in rotating coordinate system, it is on force and there exists mass on all three accelerations with the addition of translational force. Through the example that was mentioned earlier, all of it illustrates that non-inertial reference frames generate apparent force due to the acceleration of the frame itself. So understanding the fictitious force is important to accurately describe the motion in the non-inertial system.